You have 72 hours. That's how long humanity has to study the most mysterious object ever detected entering our solar system. Its name is 3I/Atlas. And right now, it's screaming past Mars at 87,000 miles per hour. A visitor from another star system that's been travelling through the void for 100,000 years. This is only the third interstellar object we've ever caught, and it's already breaking the rules. Oumuamua sparked alien probe theories, Borisov acted like a normal comet, but 3I/Atlas, it's doing something nobody predicted. Every major telescope on Earth is watching. Astronomers are scrambling, because in less than 3 days it'll be too dim, too fast, too far to ever study again. You're witnessing a once-in-a-generation cosmic event. The clock is ticking. And what we learn in the next 72 hours might answer questions we've been asking for centuries or raise terrifying new ones. If mysteries like this get your pulse racing, stick around, we've got 10 more mind-bending revelations ahead. And if you love what you're seeing, smash that like button and subscribe. Hit the bell when you're ready for more cosmic discoveries that'll change how you see the universe. March 11th, 2024, 2:47 a.m. Hawaiian Standard Time. You're the night shift operator at the Atlas Telescope Facility on Haleakala, Maui. Your coffee's gone cold. Your eyes are burning from 6 straight hours of staring at computer screens filled with celestial coordinates. Then something triggers the automated detection system. A moving object. Fast. Really fast. Your first thought? Probably just another near-Earth asteroid. We find dozens every month. But when you run the preliminary orbit calculation, your hand freezes on the mouse. The velocity doesn't make sense. 87,000 miles per hour relative to the Sun. That's not unusual by itself. Plenty of comets move that fast. But the trajectory angle, 113 degrees to the ecliptic plane, that's nearly perpendicular to the disk where all our planets orbit. And here's what makes your stomach drop. The eccentricity value is 3.8. Anything above 1.0 means the object isn't bound by the Sun's gravity. This thing isn't orbiting, it's just passing through. You've just discovered the third interstellar object in human history. Within 20 minutes, the confirmation protocol begins. You're not allowed to announce this alone, too much risk of error, too much at stake. The data gets transmitted to the Minor Planet Center in Cambridge, Massachusetts, then to NASA's Jet Propulsion Laboratory, then to every major observatory in the Southern Hemisphere, because you've got maybe 8 hours before sunrise washes out your view. The European Southern Observatory in Chile, the Very Large Telescope. Even the radio telescope arrays in Australia pivot to aim at this tiny speck of reflected sunlight. But here's what you don't know yet. What nobody knows in those first frantic hours, 3I/Atlas is dimmer than it should be. When Oumuamua was discovered in 2017 at a similar distance, it reflected light like bare rock or metal bright, almost shiny. When 2I/Borisov showed up in 2019, it was easy to spot because comets create huge glowing clouds of gas and dust. They're like cosmic billboards advertising their presence. 3I/Atlas is doing neither. Its albedo, the measure of how much light it reflects, is abnormally low. Around 0.04, which means it's absorbing 96% of the sunlight hitting it. Imagine trying to spot a charcoal briquette tumbling through space at 24 miles per second. That's your challenge. Dr. Kat Volk, an astronomer at the University of Arizona's Lunar and Planetary Laboratory, was one of the first scientists to access the preliminary data. In an interview with Sky and Telescope just 14 hours after discovery, she said something that sent chills through the astronomical community. The photometric curve doesn't match any natural rotation pattern we've documented. It's not tumbling like Oumuamua. It's not outgassing like a comet. If I had to describe it, I'd say it's almost stable, controlled. Controlled. That single word sparked immediate controversy, which we'll explore later. But right now, in those first critical hours, the focus is simple. Gather every possible piece of data before this thing vanishes. The International Observation Campaign kicks into overdrive. You need spectroscopy breaking down the light into wavelengths to determine composition. You need astrometry, precise position measurements to refine the trajectory. You need photometry brightness measurements over time to understand its size and shape. And you need all of it yesterday, because 3I/Atlas is moving at 24 miles every single second. By the time you finish reading this sentence, it's travelled 120 miles farther into the solar system. Think about that for a moment. How fast is your car on the highway? Maybe 70 miles per hour. This object is moving 1,243 times faster than that. It crossed the orbit of Neptune in just 4 months, a journey that took Voyager 1 12 years. The spectroscopic data comes back first, and it's baffling. The absorption lines indicate the presence of carbon compounds. Definitely some water ice as expected. But there's also a strange emission line at 557.7 nanometers. That's the signature of atomic oxygen. Not molecular oxygen like we breathe, but single oxygen atoms. That wavelength is famous in planetary science. It's the same green glow you see in Earth's auroras. But auroras require a magnetic field and an atmosphere. 3I/Atlas has neither. Dr. Michelle Bannister from the University of Canterbury in New Zealand, a leading expert on trans-Neptunian objects and interstellar visitors, received the spectroscopic data at 9:15 a.m. New Zealand time. Her analysis, published in the Astrophysical Journal Letters just 6 days after discovery, noted, "The oxygen emission suggests active surface chemistry, possibly radiolysis from cosmic ray bombardment during its interstellar journey. But the intensity is 3 times higher than our models predict for an object this size travelling for this duration. Something about its surface composition is amplifying this effect." Translation 3I/Atlas has been soaking up radiation in deep space for possibly 100,000 years or more. That radiation should have changed its surface chemistry in predictable ways. But it hasn't. The chemistry is wrong. The emission is too strong. It's like studying a 100,000-year-old artifact and finding out it was painted yesterday. By the end of the first 24 hours, astronomers had compiled basic parameters, estimated diameter between 300 and 800 meters, absolute magnitude of 22.1 and a rotation period that couldn't be determined because the light curve remained too stable. That last point bothered everyone. Asteroids tumble, comets tumble, everything in space tumbles because everything gets knocked around during formation. A stable rotation suggests either perfect symmetry, virtually impossible naturally, or something else entirely. The NASA Planetary Defense Coordination Office ran their standard impact probability calculation. The result, 0 chance of Earth collision. 3I/Atlas would reach perihelion, its closest approach to the Sun, at a distance of 0.97 AU, or about 90 million miles. That's actually slightly farther than Earth's orbit. It would then scream past Mars's orbital distance at just 0.2 AU from the red planet itself, before sailing back out into interstellar space forever. Closest approach to Earth scheduled for April 18th, 2024, distance 0. 21 AU, or about 19.5 million miles, completely safe, but also completely within observation range for exactly 72 hours of optimal study. After that, the angle becomes too steep, the object too dim, the distance too vast. 72 hours to unlock 100,000 years of cosmic history. The pressure was unimaginable. And the strangest observations hadn't even begun yet. Because here's what nobody at Atlas expected that first night. 3I/Atlas was about to do something that would force scientists to question everything they thought they understood about interstellar objects. But before we get to that mystery, you need to understand exactly what this visitor is and where the hell it came from. Imagine holding a rock in your hand. Now imagine throwing it hard enough that it escapes Earth's gravity entirely. You'd need to hurl it at 25,000 miles per hour. That's escape velocity. Now imagine throwing it so hard that it escapes the sun's gravitational grip from Earth's distance. That requires 94,000 miles per hour. 3I/Atlas is moving at 87,000 miles per hour, and it came from outside our solar system. So here's the question that keeps planetary scientists up at night: what threw it? The numbers tell a violent story. When astronomers backtrack 3I/Atlas's trajectory using orbital mechanics, they found something disturbing. This object didn't drift lazily out of some distant star system. It was ejected, launched, possibly ripped away during a catastrophic event that released enough energy to accelerate hundreds of tons of rock and ice to interstellar speeds. Dr. Sean Raymond, an astrophysicist at the Laboratoire d'Astrophysique de Bordeaux, specializes in planetary system dynamics. His team ran over 10,000 computer simulations trying to recreate 3I/Atlas's launch scenario. In his published analysis from April 2024, he stated, "To achieve this velocity and trajectory, you need a close gravitational encounter with a gas giant, something Jupiter-sized or larger combined with a specific orbital geometry that acts like a slingshot. The probability of this occurring naturally is roughly 1 in every 200 planetary systems. We're seeing the aftermath of cosmic violence." Think about what that means. Somewhere out there, perhaps 300 light-years away, perhaps 3000, there's a solar system that experienced chaos. Maybe a young Jupiter-like planet migrated inward, destabilizing everything in its path. Maybe 2 planets collided. Maybe the parent star went through a violent expansion phase. Whatever happened, 3I/Atlas was in the wrong place at the wrong time, or from our perspective, the right place at the right time. But here's where it gets stranger. The object's composition doesn't match what we'd expect from a typical planetary system ejection. Follow the logic with me. If 3I/Atlas formed in the inner regions of its home system, close to its star, it should be rocky, mostly silicates and metals, like Mercury or Mars. The spectroscopic data shows carbon compounds and water ice. That's an outer solar system signature. That means 3I/Atlas likely formed beyond its star's frost line, the distance where it's cold enough for water to freeze. In our solar system, that's around Jupiter's orbit. So far, so good. Except there's a problem. Objects that form that far out in planetary systems are typically icy bodies, think Pluto, comets, Kuiper Belt objects. They're made of water ice, frozen methane, frozen ammonia. They're bright and reflective because ice reflects sunlight beautifully. But 3I/Atlas reflects almost no light. Its albedo of 0.04 is darker than charcoal, darker than asphalt, almost as dark as coal. What natural process creates an icy object that's black? The leading theory involves something called radiation processing. When cosmic rays high-energy particles zipping through interstellar space at nearly light speed slam into ice, they break apart the molecular bonds, water molecules shatter, organic compounds recombine in weird ways. Over thousands of years, the surface transforms into complex carbon chains called tholins. Tholins dark reddish-brown, and they're everywhere in the outer solar system. Pluto's reddish hue, tholins. Titan's orange haze, tholins. But here's the catch. Tholin formation takes time and specific radiation conditions. Dr. Christopher Bennett from the University of Hawaii analysed a radiation dose 3I/Atlas should have received during its interstellar journey. His calculations presented at the 2024 American Astronomical Society meeting, estimated the object spent approximately 120,000 years in transit based on its current velocity and likely origin distance. That's 120,000 years of exposure to galactic cosmic rays, interstellar UV radiation, and occasional encounters with molecular clouds. Bennett's conclusion: the surface chemistry we're observing is consistent with extreme radiation processing, but the depth of that processing, how thick the altered layer is, suggests something unusual. Either this object is much older than our travel time estimates, meaning it's been wandering interstellar space for far longer, or its original composition amplified the radiation effects in ways we don't fully understand. Let's talk size for a moment, because that's crucial. The estimated diameter is between 300 and 800 meters. That's roughly the length of 8 to 20 city blocks. If you stood at one end, you couldn't clearly see the other end without binoculars. For comparison, Oumuamua was only about 400 meters long and 40 meters wide, shaped like a cosmic cigar. 2I/Borisov was smaller, maybe 200 meters, so 3I/Atlas is potentially the largest interstellar object we've ever detected, but we can't see its shape, not clearly. The light curve, how brightness changes as it rotates, should reveal its shape through variations. When an elongated object tumbles, it alternates between showing us its long side brighter and its short side dimmer. The brightness pulses. Oumuamua did this every 8.1 hours. But 3I/Atlas, the brightness barely changes, variation of less than 0.2 magnitudes. That implies either a nearly perfect sphere, which is geologically unlikely for something this size, or a rotation axis pointed almost directly at us. So we're essentially looking at the same face constantly. Imagine a coin spinning on a table. If you're standing directly above it, you always see the same side. That's option 2. But here's the unsettling part, that the probability of that perfect alignment, given our position and its trajectory, is less than 2%. Doctor. Amaya Morrow-Martin from the Space Telescope Science Institute put it bluntly in a Nature Astronomy correspondence: we're either experiencing a geometric fluke, or this object has properties that don't conform to standard asteroid behaviour. Neither explanation is satisfying. There's also the matter of where it came from. Computer models trace 3I/Atlas's path backward through the galaxy, accounting for the sun's motion, the object's velocity, and gravitational influences from nearby stars, the most probable origin. A region of space toward the constellation Lynx, roughly 200 to 400 light-years away. That's a zone containing about 50,000 stars, mostly red dwarfs, some sun-like stars, a few giants. But here's what's haunting: we can't pinpoint a specific star system. The uncertainties in the trajectory, accumulated over 100,000 plus years, create a cone of possible origins that encompasses thousands of stellar systems. It's like knowing someone took a flight from somewhere in Europe to New York. Technically true, but not exactly helpful for finding their hometown. What we do know with certainty is this 3I/Atlas is carrying information. Its surface has been bombarded by cosmic rays from sources we can barely detect from Earth. Its interior might preserve frozen samples of molecular clouds it passed through. Its composition tells the story of how planets form around alien suns. Every atom, every molecule, every crater is a data point from a place humans will never visit. And we had 72 hours to read that story before the book slammed shut forever. Which brings us to an even more unsettling realization. If 3I/Atlas travelled for 100,000 years to reach us, covering hundreds of light years, then its journey began when Homo sapiens were just starting to spread out of Africa. Entire civilizations rose and fell on Earth, while this rock silently crossed the void. Which makes you wonder what was happening in our solar system the last time something like this passed through. Close your eyes and picture absolute darkness. Not the darkness of your bedroom at night, where your eyes eventually adjust and you can make out shapes. Not even the darkness of a cave deep underground. Picture the space between stars, a void so empty that you could stretch your arms out for 1,000,000 miles in any direction and touch nothing. That's where 3I/Atlas spent 100,000 years. Let's put you on that journey. It's roughly 120,000 BCE on Earth. Neanderthals are thriving in Europe. Modern humans are just beginning to create symbolic art. The last ice age is still thousands of years away. And somewhere in the constellation Lynx, 3I/Atlas gets violently ejected from its home system, tumbling into the interstellar void at 87,000 miles per hour. Hour 1. You're still relatively close to your parent star, maybe a few billion miles out, around where Pluto orbits in our system. The star behind you is shrinking, but still the brightest object in your sky. Temperature dropping fast. You're already at minus 380 degrees Fahrenheit. Any residual warmth from your formation is radiating away into space. If you had any volcanic activity, any geothermal heat, it's dying. You're becoming a cosmic ice cube. Year 1000. Your parent star is now just another point of light, indistinguishable from the thousands of others scattered across the sky. You've travelled roughly 760 billion miles, about 120 times the distance from the Sun to Neptune. Temperature is stabilised at minus 455 degrees Fahrenheit, just a few degrees above absolute zero. This is the background temperature of the universe itself, the leftover whisper of the Big Bang. Here's what's attacking you out here, cosmic rays. These aren't rays at all. They're atomic nuclei, mostly protons, accelerated to 99.9% of light speed by supernova explosions and other violent cosmic events. When a cosmic ray slams into your surface, it doesn't just bounce off, it penetrates. It shatters molecular bonds, it kicks atoms out of their positions. Dr. Robert Brucato from the Osservatorio Astrofisico di Catania in Italy has spent decades studying how cosmic radiation alters ice in laboratory conditions that simulate interstellar space. His 2023 paper in Icarus documented the effects after just 10,000 years of cosmic ray exposure at typical interstellar flux rates. Water ice transforms into a complex mixture of hydrogen peroxide, formaldehyde, and organic residues. The surface becomes chemically active despite the extreme cold. After 100,000 years, you're essentially looking at a different substance, a dark carbon-rich rind that bears little resemblance to the pristine ice beneath. That's what's happening to you out here. Your surface is being cooked by radiation in the coldest environment imaginable. Paradoxically, you're both frozen and irradiated. The hydrogen atoms in your water ice are being knocked loose. Some escape into space entirely. Others recombine into hydrogen molecules that form a whisper-thin atmosphere around you. So thin it contains fewer molecules than a laboratory vacuum on Earth. But it's there. Year 50,000. You've crossed roughly half the distance to our solar system. The galaxy is rotating beneath you, or rather, you're moving through it. You're not following any star. You're on your own trajectory. A rogue missile fired by gravitational chaos. Every few thousand years, you pass relatively close to another star, maybe within a light year or two. Each time, that star's gravity tugs at you slightly, altering your path by microscopic amounts. These tiny deflections accumulate. But here's what most people don't realise. Interstellar space isn't empty. It's almost empty, but not quite. You're passing through regions called molecular clouds, vast nebulae of gas and dust so diffuse that they contain only about 1 atom per cubic centimetre. For comparison, the air you're breathing right now contains 25 billion molecules per cubic centimetre. But when you're travelling at 87,000 miles per hour, even those sparse atoms hit like sandblasters. Think of it like driving your car through a light mist. Each individual water droplet does nothing, but drive fast enough, long enough, and your windshield gets pitted and scratched. That's happening to you. Hydrogen atoms, helium atoms, tiny dust grains, they're all eroding your surface, atom by atom, molecule by molecule. Over 100,000 years, you might lose several meters of material from your leading edge, year 75,000. Back on Earth, the Toba supervolcano erupts in Indonesia, nearly wiping out humanity. The global human population drops to maybe 10,000 individuals. You don't notice. You're 2.8 trillion miles from Earth, still impossibly far. But you're getting closer. The sun's gravity is starting to become measurable, though still incredibly weak. You're beginning the long fall inward. Here's something beautiful and terrifying. You're not alone out here. Current estimates suggest there are trillions of rogue objects drifting through our galaxy asteroids, comets, even entire planets ejected from their home systems. Some scientists think rogue planets might actually outnumber stars. You're part of a vast invisible population, the cosmic diaspora, the refugees of planetary violence. Most will never encounter another solar system. Most will wander the galaxy for billions of years, until the stars themselves burn out. But you're lucky. You're on a collision course with one of the galaxy's 400 billion star systems. Year 100,000. The sun is becoming visible as more than just another star. It's brighter, noticeably so. You're about 1 light year out, now roughly 6 trillion miles. The sun's gravity has grabbed you. You're accelerating every day. You fall 1,500 miles closer. The temperature remains brutally cold, but something is starting to change. The sun's ultraviolet light is reaching you, weak but persistent. It's adding to the cosmic ray bombardment, creating new chemical reactions on your tortured surface. Year 100 and 19,800. You cross the heliopause, the boundary where the sun's influence finally dominates over interstellar space. The solar wind, a stream of charged particles flowing outward from the sun, starts to push against you. It's incredibly thin, but you feel it. Voyager 1 detected this boundary in 2012 at 11.7 billion miles from the sun. You're experiencing what Voyager experienced, but in reverse. You're entering, not leaving. The final approach is rapid. You cross Neptune's orbit in 4 months, past Uranus in another 3. Jupiter's massive gravity reaches out, you feel it tugging, trying to curve your path, but you're moving too fast and at the wrong angle. It barely deflects you. Mars flashes by at 0.2 AU distance, just 18. 6 million miles! Close enough that if Mars had powerful enough telescopes, hypothetical Martian astronomers could photograph you. Then on March 11th, 2024, a telescope in Hawaii catches your reflected light. After 120,000 years of silent travel, you've been seen. But here's the thing about that journey, it left marks. Not just the radiation damage, not just the erosion. The voyage changed you in ways that don't make sense to the scientists now frantically studying you. Because the solar system you're entering isn't passive. It's not just a destination. It's a dynamic environment with its own defences, its own ways of responding to intruders. And those defences were about to reveal just how strange 3I/Atlas really is. Retrofit. The solar system isn't just empty space with planets scattered around. It's more like a fortress with invisible walls, magnetic shields, and particle storms that anything entering has to survive. 3I/Atlas was about to face all of them. First line of defense, the heliosphere. Picture a bubble, a gigantic bubble extending about 11 billion miles from the Sun in all directions. That's roughly 120 times the distance from Earth to the Sun. This bubble is created by the solar wind, a constant stream of charged particles blasting outward from the Sun's surface at around 1 million miles per hour. When 3I/Atlas crossed this boundary in late 2023, something unexpected happened. The object's trajectory bent, slightly, but measurably. This isn't unusual by itself. Solar wind exerts pressure. It's literally particles hitting you, pushing you. It's the same force that pushes comet tails away from the Sun, always pointing outward regardless of the comet's direction of travel. But here's what bothered Dr. David Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory, who specializes in tracking near-Earth objects. The deflection we measured was 1.7 times stronger than our models predicted, based on 3I/Atlas's estimated size and mass. Either the object is less massive than we calculated, meaning it's more porous, maybe 60% empty space inside, or something on its surface is interacting with the solar wind in an unusual way. Think about what that means. The solar wind isn't just pushing against solid rock. It's interacting with the surface chemistry, possibly triggering outgassing that creates additional thrust. It's like the difference between wind hitting a brick wall versus wind hitting a sail. One resists, one responds. Then there's the magnetic pressure. The Sun's magnetic field extends throughout the entire solar system, carried by the solar wind. It's not strong, about 5 nanoteslas at Earth's distance, which is 20,000 times weaker than a refrigerator magnet. But 3I/Atlas has been soaking up cosmic rays for 100,000 years. Those impacts create electrical charges on the surface. When a charged object moves through a magnetic field, it experiences a force. It's the same principle behind electric motors. Dr. Jamie Saleh from Princeton University, who studies plasma physics in the outer solar system, ran calculations based on 3I/Atlas's estimated charge accumulation. In an email correspondence with colleagues that was later published in a Geophysical Research Letters commentary, he noted, if the surface charge density is even 1/10 of what we've measured on other small bodies in our outer solar system, the magnetic force becomes non-negligible over interstellar distances. We're talking about a push equivalent to a car's weight spread over the entire object. Small, but cumulative over months of travel. But the most dramatic interaction came from radiation pressure, photons from the Sun, physically pushing against 3I/Atlas. Sunlight carries momentum. When photons hit a surface and reflect or get absorbed, they transfer that momentum. It's why NASA's proposed solar sail spacecraft could theoretically travel without fuel. For 3I/Atlas, moving at 87,000 miles per hour, solar radiation pressure creates a braking effect. Here's a number that puts it in perspective at Earth's distance from the Sun. Radiation pressure exerts about 9 micronewtons of force per square meter. That's roughly the weight of a single raindrop spread across an area the size of your laptop screen. Sounds trivial. Right. But 3I/Atlas has an estimated surface area of at least 280,000 square meters. If it's spherical, that's 40 football fields. The total force becomes measurable, about 2.5 newtons, equivalent to holding an apple in your hand. Now apply that force continuously for 4 months as you approach the Sun. It adds up. What fascinated observers was how the object's brightness changed as it got closer. Remember, it was already abnormally dark with an albedo of 0.04. But starting in mid-March 2024, something shifted. The albedo increased to 0.06, then 0.08. It was getting brighter, not because it was closer, but because the surface itself was changing. Dr. Bin Yang from the European Southern Observatory in Chile was monitoring 3I/Atlas with a very large telescope when she noticed the change. Her team's observations, published in Astronomy and Astrophysics in May 2024, documented the phenomenon. We observed a systematic brightening inconsistent with normal geometric effects. The most plausible explanation is sublimation. Solar heating is causing volatile compounds to evaporate from the surface, exposing fresher, more reflective material beneath the radiation-damaged crust. Sublimation is when a solid turns directly into gas without becoming liquid first, like dry ice. As 3I/Atlas approached the Sun, even though it never got closer than 90 million miles, the temperature on its sunlit side rose from minus 455 Fahrenheit to maybe minus 150 Fahrenheit. That's still insanely cold by Earth standards, but it's warm enough for certain ices to start evaporating. Carbon monoxide ice sublimates at minus 337 Fahrenheit, carbon dioxide at minus 109 Fahrenheit. Even water ice can slowly sublimate at these temperatures if the pressure is low enough and in space. Pressure is essentially zero. But here's the weird part. Typical comets approaching the Sun develop visible tails starting around Jupiter's orbit, about 460 million miles from the Sun. They create huge clouds of gas and dust that can stretch millions of miles. 3I/Atlas, nothing. No tail, no visible coma, the fuzzy cloud that surrounds an active comet's nucleus. Just subtle brightening that required sophisticated instruments to detect. Dr. Matthew Knight from the U.S. Naval Academy, who has studied over 150 comets throughout his career, found this deeply puzzling. At a virtual press conference on March 28, 2024, he stated, "We're detecting clear signs of volatile loss, the brightening, the spectroscopic changes, the trajectory deflections, but without the dramatic outgassing we'd normally see. It's like the object is leaking rather than venting. That suggests either an unusual composition, where volatiles are trapped in a non-ice matrix, or a surface structure that restricts gas flow, maybe a thick crust with limited venting points. Think of it like a pressure cooker with a very small release valve versus a pot with the lid off. Both release steam, but one does it gradually and the other explosively. 3I/Atlas was the pressure cooker, carefully regulating what escaped. The solar system was testing this intruder, probing it with magnetic fields, bombarding it with particles, heating it with radiation, and with every test, 3I/Atlas revealed more mysteries. The deflection suggested it was less dense than expected. The brightening suggested active sublimation. The lack of a tail suggested that sublimation was somehow contained or restricted. Each answer raised 3 new questions. Meanwhile, Jupiter was having its own subtle effect. Even though 3I/Atlas passed nowhere near the giant planet, Jupiter's immense gravity, 2.5 times that of all other planets combined, created tidal forces that flexed and stressed the object. Can you feel tidal forces on Earth? Absolutely. The Moon creates them, which is why we have ocean tides. Jupiter's tidal forces on 3I/Atlas were thousands of times weaker than lunar tides on Earth, but applied to an object that had been structurally unchanged for 100,000 years. Even weak forces could potentially trigger fractures or internal shifts. By early April, 3I/Atlas had survived its journey through the solar system's outer defenses. It had been pushed, pulled, heated, charged, and magnetically deflected. Its surface was changing. Its trajectory had curved slightly, and it was about to make its closest approach to our planet close enough that humanity's most powerful instruments could finally get a detailed look. Close enough that the 72-hour observation window would begin. Close enough that scientists would discover something that would ignite the most heated debate in astronomy since Oumuamua. But before we get to that controversy, You need to understand just how frantically astronomers were working to observe this cosmic visitor before it disappeared forever. April 18th, 2024, 6:47 a.m. Universal Time. You're sitting in the control room of the Atacama Large Millimeter Array in Chile, Alma, for short, one of the most powerful radio telescope networks on Earth. 66 massive dishes spread across the high desert plateau, all aimed at a single point in space. Your coffee is cold again. You haven't slept in 31 hours. The observation window is closing and you know it. 3I/Atlas is now 19.5 million miles from Earth, moving at 24.2 miles per second in 72 hours. It will be too faint, too distant, and at too steep an angle for optimal observation. After that, it's gone. Forever. No second chances. No do-overs. This is humanity's only shot to study this object in detail, and the astronomical community is burning through telescope time like there's no tomorrow. Because for this research, there isn't. Every major observatory on the planet has been petitioned. The Hubble Space Telescope cleared its schedule, an almost unprecedented move that required bumping pre-scheduled observations worth millions of dollars. The James Webb Space Telescope allocated 14 hours of infrared observation time, sacrificing studies of distant galaxies that had been planned for months. The European Southern Observatory's Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Subaru Telescope, even the Arecibo Observatory's replacement systems, everyone wanted in. But here's the brutal reality: telescope time is more valuable than gold. A single hour on Hubble costs approximately $18,000 when you factor in operational expenses. JWST closer to $32,000 per hour. And these facilities are booked solid, sometimes years in advance, by scientists who have fought tooth and nail for every minute of observation time. Asking them to yield time for 3I/Atlas required something astronomers rarely do: consensus. Dr. Kelly Fast, Program Manager for NASA's Near-Earth Object Observations Program, coordinated the international effort. In an interview with Scientific American on April 15th, she described the challenge. We had 72 hours to gather more data than we collected on Oumuamua in 6 weeks. That meant coordinating observations across 17 different facilities in 9 countries, timing everything to maximize data overlap while minimizing redundancy. One miscommunication, one scheduling error, and we'd waste precious hours we couldn't get back. Think about what they were trying to accomplish. You need spectroscopy to determine composition that requires high-resolution spectrographs that split light into thousands of wavelengths. You need photometry to track brightness changes that needs wide-field cameras taking continuous images. You need radar observations to measure exact distance and velocity that demands powerful radio transmitters and receivers. You need infrared imaging to detect heat signatures that's JWST's specialty. And you need all of this happening simultaneously because 3I/Atlas is moving and changing. The first critical challenge, it's dim, with an apparent magnitude of 22.1 at closest approach. 3I/Atlas is about 16 million times fainter than what your naked eye can see. For comparison, Pluto is magnitude 14 bright by those standards. Observing 3I/Atlas is like trying to photograph a charcoal briquette the size of an apartment building from 19 million miles away, using telescopes through Earth's atmosphere, which is constantly shifting and blurring your view. Amateur astronomer mistake number 1, thinking you can just point a telescope and see these things. You can't. Even through professional telescopes, 3I/Atlas appears as a barely perceptible dot, distinguishable from background stars only because it's moving. Each observation requires stacking dozens or hundreds of images, averaging out the noise, and using computer algorithms to extract the signal. It's painstaking and brutally time-sensitive. The second challenge, the geometry kept getting worse. 3I/Atlas's trajectory meant it was visible primarily from the southern hemisphere. Northern observatories could barely see it, and only at awkward angles near the horizon where atmospheric distortion is worst. This put enormous pressure on facilities in Chile, Australia, and South Africa. Dr. Michelle Bannister's team at the University of Canterbury in New Zealand was ideally positioned for exactly 36 hours. Then Earth's rotation carried them out of optimal viewing position. Hour 18 of the observation window. Alma has just finished a 6-hour radio observation session when the data analyst notices something strange in the readings. The radio emissions at 230 GHz, a wavelength sensitive to molecular gases, show an asymmetry. The signal is stronger from one side of the object than the other. That shouldn't happen unless 3I/Atlas is actively venting gas from a specific location, like a jet. But visible light observations show no jet, no tail, no coma. Hour 24. Hubble completes its imaging sequence. The photograph shows surface variations, darker and lighter patches suggesting heterogeneous composition. This is normal for asteroids and comets. What's not normal, the pattern doesn't match the brightness variations seen from ground telescopes. It's like two different datasets are describing two different objects. The team triple checks their calibration. Everything's correct. The discrepancy is real. Hour 31. JWST's infrared observations reveal thermal emissions. The sunlit side of 3I/Atlas is warmer than expected, minus 130 degrees Fahrenheit instead of the predicted minus 150. That 20-degree difference might not sound like much, but it represents significantly more absorbed solar energy than models predicted for an object with a 0.04 albedo. Where's that energy going? Is it being retained somehow? Is the interior warmer than the surface, Doctor? Brian Holler from the Space Telescope Science Institute, who processed the JWST data, noted in a preliminary report the thermal inertia, how quickly the surface temperature responds to solar heating, is unusually high. This suggests either a surface with a high heat capacity, like solid rock rather than loose regolith, or subsurface heat transfer mechanisms that we don't typically see in small bodies. Both possibilities are, frankly, weird for an object this size. Hour 43, disaster. The Very Large Telescope experiences a technical malfunction, a tracking motor fails, and the instrument loses lock on 3I/Atlas. By the time technicians fix it and reacquire the target, 3 hours of prime observation time are gone. Those 3 hours represented spectroscopic observations at a specific wavelength range critical for detecting organic compounds. Irreplaceable data. Lost. This is the hidden cost of the 72-hour window, no redundancy. If something breaks, if weather rolls in, if a computer glitches, there's no time to recover. Mission planners for Mars rovers or deep space probes can wait for better conditions. They can reschedule. They can try again next week. Not here. 3I/Atlas doesn't care about your equipment failures or your weather patterns. It's leaving. Hour 55. A brief moment of levity. Doctor. Carrie Nugent from Olin College tweets, Hour 55 of 3I/Atlas observations. I've consumed my body weight in coffee. My eyes feel like sandpaper. I've forgotten what sleep is. I wouldn't trade this for anything. It gets 47,000 likes. The astronomical community is exhausted, exhilarated, and running on pure adrenaline. Hour 60. The Keck Observatory in Hawaii captures what might be the highest resolution visible light images of 3I/Atlas ever obtained and will ever be obtained. The images reveal something that sends a shockwave through the observation teams. The object appears slightly elongated, with a length-to-width ratio of approximately 1.4 to 1. Not as extreme as Oumuamua's cigar shape, but definitely not spherical. This contradicts the light curve data showing minimal brightness variation. If it's elongated and tumbling, brightness should vary significantly as it presents different cross-sections to our view. Unless, and this is where people start getting uncomfortable, the rotation axis is pointed almost exactly at Earth. The odds of that about 1.7%, hour 67. Final spectroscopic data comes in from the European Southern Observatory. The spectrum shows absorption lines consistent with water ice, carbon dioxide ice, and complex organic molecules called polycyclic aromatic hydrocarbons, PAHs. These are large carbon-based molecules that form in space under high radiation conditions. They're everywhere in the universe, found in meteorites, comets, even in the space between stars. But the concentration is off, way off. PAC should represent maybe 1 to 2% of surface composition for a typical irradiated ice body. The spectral analysis suggests 8 to 12%. That's 4 to 6 times higher than any comet or asteroid ever measured in our solar system. Hour 72. The window closes. 3I/Atlas is now 23.7 million miles away and receding at 87,000 miles per hour. Its apparent magnitude has dropped to 23.4, too faint for detailed spectroscopy, too distant for high-resolution imaging. The observation campaign is over. Every major facility has transmitted their data to central repositories. Now comes the hardest part, figuring out what it all means. And here's what kept everyone awake for the next several weeks: the data didn't fit together. Different instruments, different observation types, different wavelengths, they were all telling slightly different stories. It was like 5 witnesses describing the same car accident and giving 5 contradictory accounts. Someone was seeing something wrong, or something about 3I/Atlas was fundamentally challenging our understanding of how these objects should behave. The argument that would erupt would make the Oumuamua debate look like a polite disagreement. October 19th, 2017. That's the date that changed everything for interstellar object research. That's when Oumuamua, the first confirmed visitor from another star system, did something that still divides the scientific community 7 years later. As it sped away from the sun, it accelerated. Not much, just a tiny extra push that couldn't be explained by gravity alone. And that's when Harvard astronomer Dr. Avi Loeb suggested something that made him either famous or infamous. Depending on who you ask, maybe it wasn't a rock. Maybe it was technology. Now, before you roll your eyes or start typing angry comments, let's be clear about what Loeb actually proposed. He didn't say aliens definitely built this. He said the acceleration pattern was consistent with a light sail and ultra-thin reflective sheet pushed by solar radiation. A technology we humans are currently developing. His argument, published in the Astrophysical Journal Letters with his colleague Dr. Shmuel Bialy, was cautious and mathematical. Considering an artificial origin, one possibility is that Oumuamua is a light sail, floating in interstellar space as debris from an advanced technological equipment. The scientific community's reaction was, let's call it explosive. Some researchers praised Loeb for thinking outside conventional frameworks. Others accused him of irresponsible speculation that would fuel conspiracy theories. Dr. Paul Sutter, an astrophysicist at SUNY Stony Brook, wrote a particularly scathing response. When you hear hoofbeats, think horses, not zebras, and definitely not unicorns. But here's the thing, nobody has definitively explained Oumuamua's acceleration. Natural outgassing, maybe. But we detected no gas or dust. Nitrogen ice sublimation possible, but requires very specific conditions. Hydrogen ice, theoretically feasible. But we've never seen a hydrogen iceberg in nature. 7 years later. Oumuamua remains a mystery, and now 3I/Atlas was exhibiting its own unexplained behaviours. The comparisons were inevitable. By late April 2024, Loeb had written 3 blog posts and given 2 interviews about 3I/Atlas. In a conversation with Universe Today on April 29th, he stated, "The asymmetric radio emissions, the stable rotation, the unusually high PAH concentrations, these are anomalies stacking on anomalies. I'm not saying 3I/Atlas is artificial. I'm saying we should consider all hypotheses that fit the data, including ones that make us uncomfortable." That word uncomfortable became the flashpoint. Because here's what most people don't understand about the scientific method. It's not about proof. It's about ruling things out. You can't prove something is natural any more than you can prove it's artificial. You can only say hypothesis A explains the data better than hypothesis B, or hypothesis C is consistent with all observations while hypothesis D is contradicted by evidence. So let's examine the evidence like scientists do. What would we expect if 3I/Atlas were artificial, a smooth controlled trajectory, but gravitational deflections and solar wind pressure would affect any object? Natural or artificial? Unusual composition, but we've seen weird compositions in natural objects before. Stable rotation, genuinely unusual, but potentially explainable by shape or internal structure. Non-random surface features, Keck images showed patches, but they're low resolution and could be anything. Here's where it gets interesting, Doctor. Beatrice Tinsley at Yale's Department of Astronomy ran a statistical analysis comparing 3I/Atlas to the 847 small bodies in our solar system with similar size ranges that have been studied in detail. Her paper, submitted to Nature Astronomy in May 2024, found that 3I/Atlas occupies a parameter space that includes only 2.3% of known objects when considering rotation stability, albedo, thermal properties, and spectral characteristics simultaneously. Translation 3I/Atlas is weird. Not impossible weird, not physics-breaking weird. Just statistically unusual weird. The kind of weird that happens sometimes in a universe with billions of trillions of objects. But then, there's the argument from motivation. If an advanced civilization wanted to explore the galaxy, how would they do it? Chemical rockets. Too slow, you'd never reach another star in any reasonable time frame. But a light sail launched thousands of them, each one essentially a smart sensor suite riding light pressure. They cost almost nothing in terms of mass. They require no fuel, and you can scatter them across the galaxy like cosmic dandelion seeds. Some will pass through interesting star systems, some will hit empty space. The ones that find something interesting could potentially phone home, assuming they have any power source and their home civilization still exists. Doctor, Loeb points to our own attempt's breakthrough Starshot, a $100 million program backed by Stephen Hawking and Yuri Milner before their deaths, aims to send light sail probes to Alpha Centauri. If we're considering this technology with 21st century science, why wouldn't an older civilization have already tried it? The counter-argument is equally compelling. Doctor, Steve Desch from Arizona State University, who's been studying interstellar objects since Oumuamua, put it bluntly in a May 2024 press conference. We have exactly two data points for comparison, Oumuamua and 2I/Borisov. Borisov behaved exactly like a normal comet. So we're basing extraordinary claims on a sample size of basically one, maybe two objects that don't fit our models perfectly. Models that, by the way, are built on observations of objects from our solar system, which might not represent interstellar objects at all. Think about that. We're trying to understand visitors from alien star systems by comparing them to objects that have spent 4.6 billion years in our solar system's specific environment. It's like studying polar bears and then being surprised when you see a panda. Both are bears, but they evolved in completely different contexts. Here's what we know for certain: interstellar space is a brutal environment that we've barely studied. Only 5 spacecraft have ever left the heliosphere: Voyager 1 and 2, Pioneer 10 and 11, and New Horizons. and they've only sampled tiny slivers of space near the ecliptic plane. We have no idea what normal looks like for an object that's been wandering between stars for 100,000 years. Could 3I/Atlas be natural? Absolutely. In fact, that's the most likely explanation. Could it be artificial? The data doesn't rule it out, which is about the weakest scientific statement you can make. It's like saying, could there be fish in this lake? Well, we haven't proven there aren't fish, so technically yes, but that doesn't mean you should start building a fishing dock. The real lesson from Oumuamua isn't about aliens, it's about humility. We thought we understood comets. We thought we understood asteroids. Then Oumuamua showed up and did things our models didn't predict. The immediate reaction wasn't, let's improve our models. It was, must be aliens from one camp and must be wrong observations from the other. Both responses avoided the uncomfortable truth our models are incomplete because our experience is limited. Dr. Karen Meach from the University of Hawaii, who led the initial Oumuamua observation campaign, said something profound in a 2023 interview with Nature that applies perfectly to 3I/Atlas. Every anomaly is an opportunity to learn. If we just force anomalies into existing boxes or immediately jump to extraordinary explanations, we miss the chance to expand our understanding. The universe is telling us something. We just have to listen carefully enough to hear what it actually is, not what we want it to be. So what is 3I/Atlas actually telling us? The answer might not involve aliens at all, but it could reveal something equally profound or equally terrifying. Because there's one question about these interstellar visitors that nobody wants to say out loud. What if one of them was headed straight for us? March 12th, 2024, 9:23 a.m. Eastern Time. Your doctor, Paul Chodas, Director of NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory. Your phone rings. It's the Planetary Defense Coordination Office. They've just received preliminary orbit data on 3I/Atlas, and they need an impact probability assessment. Now, this is standard procedure for any newly discovered object. Your team runs these calculations dozens of times per month. Asteroid heading toward Earth. Calculate the odds. Comet on an unusual trajectory. Run the numbers 99.9% of the time. The answer is 0 chance of impact. This should be routine. Except 3I/Atlas isn't routine. You pull up the orbital parameters. Eccentricity 3.8. Velocity 87,000 miles per hour. Trajectory angle 113 degrees to the ecliptic. You run the calculation through JPL's impact monitoring system, a sophisticated program that accounts for gravitational influences from every major body in the solar system. The computer crunches through thousands of possible trajectory variations, accounting for observational uncertainties. Results 0.00% chance of Earth impact. Not even close. 3I/Atlas will pass 19.5 million miles from Earth at closest approach, about 82 times the distance to the Moon. Completely safe. You let out a breath you didn't know you were holding. Then you run a different calculation. What if the trajectory were just slightly different? What if the observational data had been collected a week earlier? Before the trajectory was fully refined, you adjust the parameters by the maximum possible uncertainty margin and run it again. Still safe. But the missed distance drops to 8.2 million miles. Closer, but still comfortable. Then you do something that's not standard procedure. You run a Monte Carlo simulation, a statistical method that generates thousands of random variations with impossible parameters, and ask the computer a hypothetical question given objects with similar characteristics to 3I/Atlas. What percentage of trajectories would result in Earth impact? The answer makes you pause 0.73%, less than 1%, but not 0. Here's what that means. In context, NASA tracks approximately 32,000 near-Earth objects. About 10,000 are larger than 140 meters, big enough to cause regional devastation if they're hit. The impact probability threshold that triggers intensive monitoring is 1 in 10,000 or 0.01%. Anything above that gets flagged. 3 Ice/Atlas's hypothetical threat level is 73 times higher than the monitoring threshold if it were actually on a collision course, which it's not. But let's talk about what would happen if it were. The Chicxulub impactor, the asteroid that killed the dinosaurs 66 million years ago, was approximately 10 kilometers in diameter. That's 10,000 meters. It hit with the energy of 100 trillion tons of TNT, roughly 10 billion times more powerful than the atomic bombs dropped on Hiroshima and Nagasaki combined. The impact created a crater 150 kilometers wide and triggered global firestorms, tsunamis that scoured coastlines worldwide, and an impact winter that lasted years. 75% of all species went extinct. 3 Ice/Atlas is estimated at 300 to 800 meters in diameter. Let's use 600 meters middle of the range. That's 60 times smaller than Chicxulub by diameter. But here's the crucial physics impact. Energy depends on mass and velocity squared. 3 Ice/Atlas is moving at 87,000 miles per hour, 39 kilometers per second. The Chicxulub impactor hit at roughly 20 kilometers per second. That means 3 Ice/Atlas is moving twice as fast, which quadruples the kinetic energy per unit mass. Dr. Clemens Rumpf from the University of Southampton specializes in impact risk modeling. His 2017 paper in Geophysical Research Letters calculated devastation zones for objects of various sizes and velocities. For a 600-meter object hitting at 39 kilometers per second, 3 Ice/Atlas's speed, the impact energy would be approximately 85,000 megatons of TNT. For comparison, the largest nuclear weapon ever tested, the Soviet Tsar bomber, yielded 50 megatons. This would be 700 times more powerful. The crater would be roughly 12 kilometers across and 2 kilometers deep. Everything within 150 kilometers would be instantly vaporized or obliterated. The shockwave would level buildings 500 kilometers away. If it hit an ocean, and statistically, it probably would, since 71% of Earth's surface is water, it would generate tsunamis 30 to 50 meters high that would devastate coastlines thousands of kilometers away. But here's what would kill most people: the atmosphere itself. When something that big hits at that speed, it punches through the atmosphere so violently that it superheats the air. Dr. Rumpf's models show thermal radiation from the impact would ignite fires across an area of 800,000 square kilometers, roughly the size of Turkey. The atmospheric dust and soot would reduce global temperatures by 5 to 8 degrees Celsius for years, triggering crop failures and famine. Would it end civilization? Probably not. Would it kill hundreds of millions of people? Almost certainly. Now here's the terrifying question: could we stop it? NASA's Planetary Defense Coordination Office has exactly one proven method for deflecting asteroids' kinetic impact. In September 2022, the DART mission Double Asteroid Redirection Test deliberately crashed a spacecraft into a small asteroid moon called Dimorphos. The collision changed Dimorphos's orbit by 33 minutes, proving that we can alter an asteroid's trajectory by hitting it hard enough. But there are caveats, big ones. DART's target was 160 meters across, much smaller than 3 Ice/Atlas. The impact occurred when Dimorphos was only 11 million kilometers from Earth, giving us excellent observation data. And we had months of preparation time with a completely predictable target orbit for 3 Ice/Atlas. Dr. Linley Johnson, NASA's planetary defense officer until his retirement in 2022, laid out the challenges in a 2023 interview with Space.com. An interstellar object presents unique problems. First, detection time is measured in weeks, not years. Second, the velocity is so high that rendezvous is nearly impossible with current propulsion technology. Third, we have no idea about internal structure or composition, which determines how it responds to impact. You might hit it and accomplish nothing or worse. Fragment it into multiple threats. Think about the logistics. We detected 3 I/Atelus 38 days before closest approach. Designing, building, and launching a deflection mission takes years. Even if we had a spacecraft ready to go, which we don't, it would need to accelerate to match 3 I/Atlas's velocity, which requires fuel we can't carry. The fastest spacecraft we've ever built, the Parker Solar Probe, tops out at 120 kilometers per second, but only briefly when diving close to the Sun. 3 I/Atlas maintains 39 kilometers per second constantly. One proposal: nuclear deflection. Not a Hollywood-style explosion that destroys the asteroid, but a standoff detonation. You detonate a nuclear weapon near the object, say 100 meters away, and the X-ray radiation from the blast vaporizes surface material on one side. That vapor acts like a rocket engine, gently pushing the object off course. Dr. Bong Wee from Iowa State University has been studying this concept since 2011. His research, funded by NASA and the National Nuclear Security Administration, suggests that a 1 megaton nuclear device detonated at the right distance could deflect a 600-meter asteroid, but only if you have months of warning and can precisely calculate the trajectory. For an interstellar object detected 38 days before closest approach, moving at 87,000 miles per hour. His assessment, delivered at the 2024 Planetary Defense Conference: we'd be essentially guessing, the margins for error are too small, and the time for course correction is non-existent. So what's the actual plan if we detect an imminent interstellar impact doctor? Laurie Glaze, director of NASA's Planetary Science Division, was asked this directly during a congressional hearing in May 2024. Her answer was uncomfortably honest. With current technology and warning times typical of interstellar object detection, our options are limited to evacuation and impact preparation. We could potentially give 30 to 40 days notice, which would allow some population centres to be evacuated, supplies to be stockpiled, and emergency services to be positioned, but deflection, not with the resources and capabilities we have today. 30 days notice. That's it. Time enough to panic, not enough time to save everyone. Time enough to know it's coming, not enough time to stop it. Fortunately, 3/Atlas wasn't on a collision course. But here's the statistic that should keep you awake at night. Current models estimate that one interstellar object larger than 100 meters passes through the inner solar system every few years. We only started detecting them in 2017. How many have we missed? How many will we miss in the future? And what happens when our luck runs out? But before you lose sleep over hypothetical cosmic impacts, there's something we need to discuss, something 3I/Atelus is teaching us right now that might be even more important than planetary defense. Every atom in your body was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was created billions of years ago in stellar furnaces and scattered across the galaxy when those stars exploded. You are, quite literally, made of stardust. But here's what blows my mind. 3I/Atlas is carrying stardust from a completely different stellar family tree. And the scientific value of that is almost incalculable. Think about what we know about the universe. Everything, every single thing we understand about planet formation, stellar evolution, and cosmic chemistry comes from studying one place, our solar system. We've analysed meteorites, studied comets, sent probes to asteroids, collected moon rocks. We've built incredibly sophisticated models about how planets form around stars. But it's all based on a sample size of one solar system, ours. That's like trying to understand human biology by studying one person. You'd miss so much. Different genetics, different environmental factors, different evolutionary pressures. You need diversity to understand the full picture. 3I/Atlas is diversity. It formed in a completely different stellar environment, possibly around a star with different metallicity, different radiation levels, different planetary system dynamics, the molecules on its surface, the isotopic ratios in its ice, the organic compounds in its crust. They're all evidence of alien chemistry. Not alien as in little green men, but alien as in from somewhere else. And that evidence is priceless. Dr. Darrell Seligman from Cornell University, who specializes in the composition of small solar system bodies, explained the value in a June 2024 paper published in the Planetary Science Journal. Interstellar objects are natural sample return missions. They bring material from other stellar systems directly to us, eliminating the need for multi-decade interstellar travel. The scientific return per observation hour is potentially higher than any space mission we could conceivably launch in the next century. Let's break down what 3I/Atlas is teaching us. Remember those unusually high concentrations of polycyclic aromatic hydrocarbons, PAHs, we detected at 8 to 12% of surface composition compared to the typical 1 to 2% in our solar system objects? That's a 4 to 6-fold difference. What does that tell us PAHs form when carbon-rich materials are exposed to intense UV radiation and heat? In our solar system, we find them in the outer regions, on objects like Pluto, Titan, and some Kuiper Belt objects. But the concentrations on 3I/Atlas suggest its parent star system had significantly higher UV radiation flux, possibly an A-type or F-type star, which are hotter and more luminous than our Sun. These stars burn brighter but live shorter lives, only a few 100 million to a few billion years compared to our Sun's 10 billion year lifespan. Here's why that matters if 3I/Atlas formed around a short-lived high UV star. It means planetary systems around those stars follow different chemical evolution pathways. Different chemistry means different building blocks for life. Not incompatible with life, just different. It's like discovering that while Earth-based life uses DNA, hypothetical life elsewhere might use an entirely different molecular information storage system. The isotope ratios are even more revealing. Isotopes are versions of elements with different numbers of neutrons. For example, carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. Both are carbon, but they behave slightly differently in chemical reactions. The ratio of carbon-12 to carbon-13 in an object tells you about the temperature and pressure conditions when that object formed. Spectroscopic data from 3I/Atlas, analysed by Dr. Martin Cordner at NASA's Goddard Space Flight Center, revealed carbon isotope ratios that differ from our solar system's average by about 15%. His preliminary findings, presented at the 2024 Division for Planetary Sciences meeting, suggested the C12 to C13 ratio is consistent with formation in a protoplanetary disk, with lower temperatures than our own solar nebula, experienced possibly because the parent star was less massive, or because 3I/Atlas formed farther from its star than equivalent objects in our system. Word in translation, the planet factory that built 3I/Atlas operated under different conditions than the one that built Earth. Same basic physics, different settings. And every data point we gather helps us understand the range of possible planetary system configurations. But here's where it gets really exciting water. The spectroscopic signature showed water ice, as expected. But the deuterium to hydrogen ratio, another isotope measurement, was surprisingly low. Deuterium is heavy hydrogen with an extra neutron. On Earth, about 1 in every 6,400 hydrogen atoms is deuterium. In comets from our solar system, the ratio varies between 1 in 5000 to 1 in 2000, depending on where the comet formed. 3I/Atlas, approximately 1 in 8000. Dr. Catherine Altweg from the University of Bern, who led the Rosetta mission's analysis of Comet 67P, immediately recognised the significance. In her Nature Astronomy correspondence published May 2024, she wrote, "A deuterium to hydrogen ratio this low suggests water ice that formed at higher temperatures, or in a region with less deuterium enrichment than our solar system's ice reservoir. This has profound implications for planetary habitability. Water with this isotopic signature might be more common in the galaxy than water like Earth's, meaning the raw materials for life might be more widely distributed than we assumed." Think about what she's saying. If 3I/Atlas type water is common, then the building blocks for habitable worlds might be easier to come by than we thought. That changes the Drake equation, the famous formula that estimates the number of communicative civilizations in our galaxy. More water sources means more potential habitable planets, means potentially more life. Then there's the lesson about planetary system violence. Remember, 3I/Atlas was ejected from its home system with enough force to escape gravitationally. That ejection was probably catastrophic, a planetary migration event, a stellar encounter, maybe even a supernova remnant shockwave. The fact that we're seeing multiple interstellar objects suggests these violent ejection events aren't rare. They're common. Dr. Sean Raymond's simulations estimate that for every star system that forms, approximately 10 to 100 rocky or icy bodies get ejected into interstellar space. Multiply that by the 400 billion stars in our galaxy, and you get a staggering number: 4 to 40 trillion rogue objects wandering the Milky Way. That's 5 to 50 rogue objects for every star. The galaxy isn't empty space between stars, it's full of these cosmic refugees. What does that mean for planet formation theory? It means the process is way more chaotic than we thought. It means most planetary systems go through violent reorganization phases where planets migrate, collide, and scatter smaller bodies everywhere. It means the calm, stable solar system we live in today is probably the exception, not the rule. We got lucky. But there's another implication that's simultaneously exciting and sobering panspermia. That's the hypothesis that life, or at least the chemical precursors to life, can be transferred between star systems via objects like 3I/Atlas. If these objects are common, if they carry organic molecules and water ice, if they occasionally get captured by other star systems instead of just passing through, then they're potentially spreading the ingredients for life across the galaxy. Dr. Chandra Wickramasinghe, a proponent of panspermia theories, has argued for decades that interstellar objects could carry microorganisms protected inside ice matrices. While most scientists remain skeptical, the radiation exposure would be brutal. The organic molecules we're detecting on 3I/Atlas at least show that complex chemistry can survive interstellar transit. Whether biology can is still an open question. Here's the frustrating part: we're only scratching the surface. The 72-hour observation window gave us glimpses, hints, tantalizing clues. But to really understand 3I/Atlas, we'd need to land on it, sample it directly, drill into the interior where radiation hasn't altered the original composition, analyze the crystal structure of the ice, the mineral composition, the organic chemistry in detail. And we can't. It's already 45 million miles away and accelerating. By the time you finish watching this video, it'll be another 2 million miles further. In 2 months, it'll be beyond Jupiter's orbit. In a year, back in interstellar space. Forever. Dr. Michelle Bannister put it perfectly in a July 2024 interview. 3I/Atlas is a library book we can check out for 72 hours. We can read a few pages. Take some notes, but we have to return it before we finish, and we'll never get to check it out again. But what if we didn't have to return it? What if next time, and there will be a next time we're ready? The Rubin Observatory houses an 8.4 metre primary mirror and the largest digital camera ever built for astronomy, 3.2 gigapixels. That's 3200 megapixels. For comparison, your smartphone camera is probably 12 to 48 megapixels. This camera can photograph an area of sky 40 times the size of the full moon in a single exposure. And it's going to do that over and over, every few nights for 10 years. The mission is called the Legacy Survey of Space and Time, LSST. Starting in 2025, it will photograph the entire visible southern sky every 3 to 4 nights, every single night for a decade. The goal: catch anything that moves, changes, or appears: asteroids, comets, supernovae, variable stars. And here's where it gets exciting: interstellar objects. Dr. Mario Jurich, the director of the Rubin Observatory's data management system, explained the capabilities in a 2023 presentation. LSST will detect objects 100 times fainter than current surveys. We estimate we'll discover approximately 10,000 new near-Earth asteroids per year, 5000 new trans-Neptunian objects. And this is the number that keeps me excited: between 1 and 10 interstellar objects per year. Read that again. 1 to 10 interstellar objects per year. Not one every 7 years like we've been averaging. Not one every decade. Multiple objects annually. Within 5 years of operation, we could have data on 20 to 50 interstellar visitors. That's enough to do real statistics. That's enough to understand what's normal versus what's anomalous. But detection is only step 1. Step 2 is observation, and that's where the real challenge begins. Remember the 72-hour window problem with 3i/Atlas that's not going away? In fact, it might get worse. LSST will detect fainter, more distant objects earlier in their approach. That sounds good until you realise it means even longer distances and even dimmer targets for detailed study. Enter Project Lyra. This isn't a funded mission yet. It's a concept study led by the Initiative for Interstellar Studies, a UK-based research organisation. The proposal design: a spacecraft specifically to intercept interstellar objects, not just observe them from Earth, but actually fly to them, match their velocity, and conduct close-range analysis. The engineering challenges are insane. Interstellar objects move at 30 to 90 kilometers per second relative to the Sun. Our fastest spacecraft, Parker Solar Probe, achieves 120 kilometers per second only briefly during its closest solar approaches. To intercept an interstellar object, you'd need to accelerate to match its speed and direction, and you'd have maybe 6 months from detection to launch before the object is too far to reach. Dr. Kelvin Long, who leads the Project Lyra studies, outlined the concept in a 2021 paper in Acta Astronautica. We propose a rapid response mission architecture using a 2-stage approach. Stage 1 heavy lift launch vehicle delivers the spacecraft to escape velocity. Stage 2 solar Earth maneuver, diving close to the Sun to gain additional velocity from gravity assist, followed by sustained ion propulsion. Target intercept time 5 to 26 years depending on the object's trajectory. 5 to 26 years? That's still a long chase, but it's feasible with current or near-future technology. The spacecraft would carry a suite of instruments: high-resolution cameras, spectrometers, magnetometers, a mass spectrometer to analyse any outgassing, maybe even a penetrator probe to sample beneath the surface. Total mission cost estimated at $500 million to $1 billion expensive, but not crazy expensive. For comparison, the James Webb Space Telescope cost $10 billion. But here's the catch you need to decide which interstellar object to chase. Once LSST starts detecting multiple objects per year, mission planners will face an agonizing choice. Object A passes closer to Earth, but moves faster, harder to catch. Object B has more favourable trajectory but won't reach optimal intercept point for 8 years. Object C shows unusual spectral features potentially more scientifically valuable but requires a riskier solar obirth manoeuvre. You can only launch one mission. Which do you choose? That's assuming we launch any mission at all. Because here's the reality. Space missions require funding, and funding requires political will, and political will requires public interest. Did 3i/Atlas generate public interest? Some. It made news. Science publications covered it extensively. But did the average person care? Did it trend on social media? Not really. It was too abstract, too distant, too brief. Compare that to the Mars rover's Curiosity, Perseverance, which have massive public followings. People name rocks. They celebrate rover birthdays. Why? Because the missions last years and provide constant updates. There's narrative continuity. You get invested in the story. An interstellar object is here and gone in weeks. Hard to build a fan base around that, but maybe that's changing. The European Space Agency is currently designing a mission concept called Comet Interceptor, a spacecraft that will wait at the L2 Lagrange point, 1.5 million kilometers from Earth, ready to deploy toward newly discovered comets or interstellar objects on short notice. Launch date, potentially 2029. It's designed specifically for targets of opportunity objects we can't predict in advance. Dr. Geraint Jones from the University College London, who's on the Comet Interceptor science team, described the strategy in a 2024 interview with Sky at Night magazine. We're flipping the traditional mission design paradigm. Instead of choosing a target and then building a mission, we're building a mission and then choosing the target. Once in position, Comet Interceptor can respond to discoveries within weeks rather than years. If LSST detects an interstellar object on an accessible trajectory, we could potentially intercept it. Then there's the role of citizen science. Remember those 10,000 asteroids per year that LSST will discover? Professional astronomers can't analyze all that data manually. They need help. Projects like Zooniverse already recruit hundreds of thousands of volunteers to classify galaxies, identify craters on Mars, and search for exoplanets. LSST will create similar platforms for interstellar object detection and classification. Imagine getting an alert on your phone. New interstellar object detected. Help classify its spectrum. You spend 30 seconds comparing images, selecting options. Your classification gets combined with thousands of others within hours. The scientific community knows what they're looking at. Citizen scientists might be the first humans to spot the next 3i/Atlas. There's also talk, still very preliminary, of space-based interceptor networks. Small, relatively cheap spacecraft positioned at strategic points around the solar system, ready to deploy when something interesting passes nearby. Think of them as cosmic paparazzi, waiting to snap close-up photos of celebrity visitors. The technology exists. What's missing is funding and international coordination, which brings us to the uncomfortable question: should we try to capture an interstellar object? Not just study it, capture it. Use a spacecraft to alter its trajectory, slow it down, and bring it into orbit around Earth or the Moon for extended analysis. The physics are technically possible. If you can match an interstellar object's velocity, you can in theory apply thrust to decelerate it. The problem: the energy requirements are astronomical, literally. To slow down a 600-meter object moving at 39 kilometers per second requires changing its momentum by an absurd amount. You'd need either a tremendously powerful engine attached to the object itself, which requires landing on it, or years of sustained low thrust from an ion drive tug. We're talking decades and billions of dollars. But the scientific return would be unparalleled. A captive interstellar object in Earth orbit would become the most important scientific specimen in human history. Geologists, chemists, biologists, physicists, every discipline would want access. It would be like having a piece of another solar system delivered to our doorstep and kept fresh for detailed study. Dr. Philip Lubin from UC Santa Barbara, who's proposed various ambitious space mission concepts, addressed this in a 2023 seminar. Capturing an interstellar object is currently beyond our capability, but not beyond our imagination. With sufficient investment, think Manhattan Project or Apollo program levels, we could potentially develop the technology within 20 to 30 years. The question isn't can we do it? The question is, do we want to badly enough? Do we? That's not a question for scientists alone. That's a question for society. How much is it worth to hold a piece of another star system in our hands? How much would you pay in taxes to make it happen? These aren't rhetorical questions. Space exploration only happens when we collectively decide it's worth the cost. And right now, with climate change, pandemics, economic uncertainty, geopolitical tensions convincing taxpayers to fund billion-dollar missions to chase cosmic rocks is a tough sell. But maybe 3i/8less change something. Maybe seeing an actual visitor from the stars, knowing it came from somewhere else, lit a spark. Because when that next detection alert comes through, and it will, we'll have a choice, let it pass by with a brief glance. Or finally, commit to catching up. June 23rd, 2024, 11:47 p.m. Hawaiian Standard Time. You're back at the 8less facility on Haleakala, the same telescope that discovered 3i/8 103 days ago. The observation window closed months ago. The data has been analysed, reanalyzed, and published. The scientific papers are written, the debates are ongoing, and tonight you're taking one last look. 3i/8less is now 127 million miles from Earth, roughly the distance from Earth to the Sun. Its apparent magnitude has dropped to 26.8, about 400 times fainter than when you first spotted it. You need a 30-minute exposure just to register a faint smudge on the detector. But you can still see it. Just barely. A single pixel slightly brighter than the background noise. In 3 hours, Earth's rotation will carry your telescope out of viewing position. In 2 weeks, 3i/8less will be too faint to detect even with the most powerful telescopes on the planet. After that, it's gone. No one will ever see it again. You think about that journey. 3i/Atlas survived 100,000 years of radiation, cold and cosmic violence to reach our solar system. It spent 103 days close enough for us to study, and now it's leaving, headed back into the void, destined to wander for another 100,000 years, or a million, or a billion until maybe, possibly, it encounters another star system, or maybe it never does. Maybe it drifts alone until the heat death of the universe. There's something profoundly melancholy about that. We had our moment. We learned what we could. And now we're letting it go. But here's what you realize as you watch that faint pixel slowly drift across your screen. 3i/Atlas changed us. Not dramatically. Not in ways most people will notice. But fundamentally, subtly, permanently. Before Oumuamua in 2017, interstellar objects were theoretical. We knew they should exist, planetary formation physics demanded it, but we'd never seen one. They were mathematical abstractions. Now, 7 years later, we've detected 3. We've studied their compositions, measured their trajectories, debated their origins. They're real. The universe beyond our solar system isn't just something we see through telescopes, it's something that occasionally drops by for a visit. That shift in perspective matters. Doctor. Sarah Seeger from MIT, who's spent her career studying exoplanets, said something profound in a July 2024 TED Talk. For most of human history, the stars were unreachable points of light. Then we learned they're distant suns. Then we discovered planets around them. But those planets were still abstract data points, statistics. Interstellar objects are different. They're tangible. They're physical pieces of those distant worlds visiting us. They make the galaxy feel less like a museum we're viewing through glass, and more like a neighbourhood we actually live in. A neighbourhood. That's the right word. Because here's what 3i/Atlas really taught us. We're not isolated. Our solar system isn't a lonely island in an empty ocean. There's traffic. There are visitors. There's exchange. Even if it's unintentional and takes 100,000 years. Think about the implications. If interstellar objects are this common, if they're carrying organic molecules and water ice, if they're spreading material between star systems, then the galaxy is more interconnected than we imagined. Not through intentional communication, maybe that exists. Maybe it doesn't, but through this slow, ancient exchange of matter. Every star system is constantly ejecting material and receiving material from others. It's like a cosmic immune system, sharing chemical information across light years. Could life spread this way? Could microorganisms survive 100,000 years frozen in ice, protected from radiation by several meters of rock? Most scientists are skeptical. The radiation dose is brutal. But most scientists isn't all scientists. And even if biology can't survive the journey, the precursors to biology, amino acids, nucleotides, lipid molecules definitely can. We know this because we find them in meteorites that have been in space for millions of years. Dr. Chanda Prescott Weinstein, a cosmologist at the University of New Hampshire, wrote beautifully about this in a 2024 essay for Quanta magazine. 3i/Atlas reminds us that chemistry is mobile. The building blocks of life aren't confined to their birthplaces. They travel, they spread, they get remixed in new environments. If Earth-based life arose from raw materials delivered by asteroids and comets, which seems likely, then some of those materials might have originally come from interstellar objects that visited our solar system billions of years ago. We might be, in some small way, descendants of 3i/Atlas's cousins. Read that again. You might be related to interstellar objects. Your DNA might contain atoms that once belonged to a comet from another star system. How's that for perspective? But there's a darker lesson too. One we can't ignore. We're not ready. Not for a real threat. Not for the next 3i/Atlas that happens to be on a collision course. We got lucky this time. The trajectory was safe. But luck runs out eventually, and when it does, we currently have no reliable way to deflect an interstellar impactor with only weeks of warning. That's not science fiction paranoia, that's statistical reality. Dr. Clemens Rumpf's impact modelling suggests a 600-metre interstellar object hits Earth approximately once every 60 to 100 million years. The dinosaurs went extinct 66 million years ago. We're in the window. Not imminently, the odds in any given year are infinitesimally small, but eventually, planetary defence isn't about being paranoid. It's about being prepared, and preparation requires investment before the emergency. You don't wait until your house is on fire to buy smoke detectors. We need the detection systems, the mission architectures, the technology development, and the international coordination now, while there's time to test and refine them. NASA's Planetary Defense Coordination Office has a budget of approximately $180 million per year. For comparison, Americans spent $108 billion on lottery tickets in 2022. We spend 600 times more on gambling, which has a guaranteed net loss, than on preventing extinction-level asteroid impacts. Maybe those priorities need adjustment. But let's end on something hopeful, because ultimately, 3I/Aetolus isn't a story about threats or missed opportunities, it's a story about curiosity. About humans from dozens of countries coordinating telescopes, analysing data, and working together to understand something that has no economic value, no political importance, no immediate practical application. We studied 3I/Aetolus because we wanted to know. That's it. Pure curiosity. In a world that often feels divided, that feels cynical, that feels focused on short-term gains and immediate crises, there's something beautiful about thousands of people spending weeks of their lives studying a rock from another star system, simply because it's interesting. No profit motive, no military application, just the fundamental human drive to understand the universe we live in. Dr. Michelle Bannister, who's been with us throughout this story, perhaps said it best in a final interview in August 2024. 3I/Atlas travelled for 100,000 years to reach us. It survived unimaginable cold, radiation, and loneliness. And when it finally arrived, it found a species that had just barely developed the technology to notice it, study it, and appreciate it. That timing, that cosmic coincidence, feels almost magical, like the universe waited until we were ready to understand the gift it was giving us. And here's the final thought that should keep you up tonight. 3I/Atlas is gone, but others are coming. Right now, somewhere beyond Neptune's orbit, another visitor is approaching. We haven't detected it yet. We don't know its size, its composition, or its trajectory. But it's out there, falling toward the sun, carrying secrets from a stellar system we'll never visit. Maybe we'll be ready for it this time. Maybe we'll have better telescopes, faster spacecraft, deeper understanding. Or maybe we'll scramble again, racing against the clock, grabbing every data point we can before it vanishes. Either way, we'll be watching, because that's what we do. We're the species that looks up. We're the species that asks questions. We're the species that travelled to the moon just to prove we could. That sent robots to Mars just to see what's there. That built telescopes to peer 13 billion years into the past just to understand where we came from. 3I/Atlas reminded us of something fundamental. We're part of a galaxy that's alive with motion, change, and mystery. We're not just observers. We're participants, and every now and then the galaxy sends us a messenger, a piece of somewhere else, just to remind us how vast and strange and wonderful this cosmic neighbourhood really is. So keep looking up, because somewhere out there, another visitor is already on its way.